Welcome to Module 1 of this course on photovoltaic systems. In this lesson, we will explore the fundamental physics of photovoltaics, moving from the basic properties of semiconductor materials to the actual generation of direct current electrical energy. Understanding how light becomes electricity is the essential first step for any professional in this field. And now, let's hand the floor over to the professor.
Let's start with the core concept, the photovoltaic effect. This phenomenon is defined as the formation of an electrical potential difference within a system, which we call a solar cell, when it is exposed to light radiation. Technically, this is a specific type of photoelectric effect. The process follows three basic steps. First, photons from sunlight are absorbed by a semiconductor material. Second, the electrons within that material become excited and gain energy. Finally, these electrons transition from the valence band to the conduction band, becoming free to move. To understand why some materials work better than others, we must look at their energy band structure. As you can see in the diagram, materials are classified based on the energy gap, or edge, between the filled valence band and the unfilled conduction band. In metals, these bands overlap, allowing easy conduction. In insulators, the gap is too large for electrons to cross. Semiconductors, however, have a relatively small gap. For the photovoltaic effect to occur, the energy of the incident photon, expressed as E each nu, must be greater than or equal to this energy gap. This is the forbidden zone that determines the efficiency and spectral response of our cell. Silicon is the foundation of the photovoltaic industry because it is a tetravalent element that forms a stable, crystalline lattice. However, pure silicon is not a good conductor on its own. We must modify it through a process called doping. We have two types: N-type doping, where we introduce pentavalent atoms like phosphorus to create an excess of negative charge carriers or electrons, and P-type doping, where we introduce trivalent atoms like boron. This creates holes, which act as positive charge carriers that can accept electrons. In this visual representation of the silicon lattice, you can see how these impurities fit in. On the left, the boron atom creates a vacancy, or hole, in the structure. On the right, the phosphorus atom provides that extra electron. This intentional imbalance of charges is what makes the generation of electricity possible. The most critical part of a solar cell is the p-n junction. When we bring p-type and n-type materials into contact, a remarkable phenomenon occurs at the boundary. First, we have charge diffusion. Electrons move toward the p region and holes move toward the n region. This creates a depletion zone at the interface, which is empty of mobile charges. This separation results in a permanent internal electric field. This built-in field is the engine of the cell, essential for preventing the photogenerated charges from simply recombining. Finally, let's look at the complete process. When photons strike the surface, they are absorbed and create electron-hole pairs. The internal electric field we just discussed immediately drives the electrons toward the N side and the holes toward the P side. When we close the circuit through an external load, such as a lamp or a battery, the electrons flow from the N side through the circuit to reach the P side. This continuous flow is direct current, DC. This is how we convert solar energy into usable power for everything from small devices to entire electrical grids.
Thank you, Professor, for this first lesson. And thank you all for your attention. We will see you again in Module 2.